In this video, we're going to be working out 3 sample problems so you can learn all the main concepts and strategies to solve different types of collision problems. The first problem we have is the one on the left over here, where a bullet is being fired into a block for an inelastic collision. Our second one is a bouncing problem where a soccer ball bounces off the ground. And our third and final one will be on our next screen, where we have a 2D collision. All right, so starting with our first one, all we really need is our formula momentum equals mass times velocity. And the main concept that we're going to be using is the conservation of momentum, is that the total momentum of the system before the collision is the same as the total momentum of the system after the collision. All right, so what we want to do is we want to make sure we set up a before and after. And we want to make sure that the momentum that we sum up of everything in the system before the collision is the same as everything after the collision. And then we have one unknown variable that we're going to solve for by doing a little bit of math. So in this scenario, we have a 100-gram bullet that is being fired towards this wooden block. It gets embedded into the wooden block, and then both the bullet and the block are sliding together. What is their final resulting velocity? All right, first of all, I notice that this is in 100 grams. If you take 100 and divide it by 1,000, it turns into 0.1 kilograms. Okay, so let's go ahead and get that out of the way so everything is in kilograms and meters per second. Now we have the bullet before the collision, 0.1 times a velocity of 100. And then we have the mass and velocity of our block. Our block is 2 kilograms, and it looks like it's just sitting there at rest. Okay, now the sum of all the momenta before the system, before the collision, is going to be the same as the momentum afterwards. Now, both the mass of the bullet and the block can be combined. The reason for this is because if it's embedding itself into the bullet, they're going to move as one single mass, so they're now kind of like one big mass combined with some kind of final velocity. All right, from there, we just have to do a couple steps. We have their combined mass, which is just slightly over 1, we'll just call that 2.1 which is 2.1 kilograms. And then on this side, it's basically just 0.1 times 100, which is 10, plus 0, so we just have 10 kilogram meters per second of momentum over here. And then once we divide both sides by 2.1, we are done. Then we have a resulting final velocity of 4.76 meters per second. Obviously, we would assume that the bullet's velocity is going to greatly decrease, and then obviously combining with the 2 kilogram mass as well, that is going to make the velocity drop significantly. All right, so when doing any kind of elastic or inelastic collision, you want to make sure that you take the momentum of each of the objects before the collision, sum them up, make sure you're careful about directions. If you have anything going in the opposite direction, make it negative, and then do the same for everything after the collision. Take your masses and velocities of everything after the collision, and then set that on the right side of your equal sign, and then solve for whatever you need to solve for. In our second case over here, this one has some different momentum concepts that are mostly related to impulse. Now with impulse, we have 2 formulas we're going to use. We have impulse equals mass times delta V which is final minus initial velocity, and we have impulse equal to force times the impact time, which is known as delta T. All right, so with that being said, we know we are looking for an impact time when everything is all said and done. A ball is being dropped from 1.25 meters off the ground that was initially at rest. It's striking the ground, getting 100 newtons of force, and then going up at 4 meters per second. The first thing we want, though, is we do want to find the impulse. And if we need to find the impulse, then we're going to need the mass with the final and initial velocity. It looks like we have the final velocity right over here. And we just need to find the initial velocity. So we're going to go ahead and use one of our kinematic formulas. Vf squared equals Vi squared plus 2a delta y. Now, out of our different accelerated motion kinematic formulas, that's the only one that doesn't have time in it, which we like because we do not have the time in the fall. We know that we want to find that final velocity there. The starting is at rest. The acceleration due to gravity is negative 9.8. And the ball is being dropped at negative 1.25 meters as our delta y because it's displaced downward, so that's also negative. We can go ahead and multiply those three and then take the square root of them. All right, we get a velocity of 4.95 meters per second, and which is, because we took the square root, it could be positive or negative because the ball is moving downward for the first part of its motion. That is going to be negative. Okay, so that is the final velocity of from when it's dropped until it hits the ground, but it's the initial velocity for our bouncing problem because it hits the ground with a certain velocity and then bounces up at 4. All right, so we're going to use our first impulse formula and then find delta P. The mass of the ball is 2 kilograms. Whoops, that should have been in the initial part of the problem, but it's 2 kilograms times our final velocity, so it's bounced upward at 4, Vf minus Vi, and our Vi is negative 4.95, so we're basically adding those two. And then our impulse, or change in momentum, comes out to 17.9. All right, now from there we can do our final step. We're going to use our final formula right over here. Our delta P equals force times time. We know our delta P is 17.9. We know our force is 100 newtons. And we are looking for the time of impact that the ball has with the ground as it's bouncing. So we're going to go ahead and divide both sides by 100, and then we get 0.179 seconds as our time of impact. Okay, so when working on a bouncing problem, the main thing is, yeah, you're using momentum and impulse formulas, but the main thing you want to pay attention to is because it's bouncing, you're going to see a change in its signs for the velocity. It's going to change from positive to negative or negative to positive. That's definitely one of the key components to being successful in a bouncing problem. All right, let's go ahead and move to our final problem, our 2D collision. All right, now for this problem, in our two-dimensional collision, we definitely have a lot more going on here. We have a 0.5 kilogram ball moving at 4 meters per second. It's hitting this 0.3 kilogram ball that's at rest. When it hits the blue ball, it gets sent off 30 degrees from the horizontal at 2 meters per second, and then we're looking for the velocity and the theta, the angle at which the red ball is going to move. All right, we're still using the same principles that we used before, which is the total momentum of the system before the collision is equal to the total momentum of the system after the collision. So let's go ahead and do that. Now we have this one before the collision where it is 0.5 kilograms times 4, which is just going to end up being 2 kilogram meters per second. For our second one, we are going to sum it up with our second one. Our second one is 0.3 kilograms times 0 meters per second, which is obviously 0. All right, now here's the thing. When you have a two-dimensional collision, you're going to analyze the momentum being conserved along the x-axis and the y-axis. This is all horizontal motion, so the sum of the momentum in the x direction is 2 kilogram meters per second. The sum of the momenta in the vertical direction is 0 because there is no vertical motion before the collision. All right, now that's going to be a key component to solving the problem. All right, now after the collision, we have this blue ball that's going 2 meters per second at a 30-degree angle. Now what we want to do is we want to go ahead and make a triangle off to the side. And since the mass is 0.3 for our blue ball, if I do 0.3 times 2, it gives me its total momentum of 0.6. Okay, out of that 0.6, we're going to make a right triangle and find how much of the momentum is directed horizontally and how much of it is directed vertically. So we are going to make our little triangle, and we want to use the hypotenuse and then find the vertical component and the horizontal. The vertical component is opposite of the 30-degree angle, and we want to use the hypotenuse. So we're going to do sine of 30 degrees equals opposite over the hypotenuse. Multiply both sides by 0.6, and then our y component comes out to 0.3. We're going to use cosine for our x component because it's adjacent to our 30-degree angle. So cosine of 30 degrees equals x over our 0.6. Multiply 0.6 on both sides, and then I get 0.52 for my x component. All right, now with that being said, we know that on the left side, we have 2 kilogram meters per second in the x direction, and then we have 0.52 kilogram meters per second of momentum from our blue ball, which means that if we find the difference between those two, then we could find the x component for our red ball, which is basically just subtracting 0.52 from both sides. In that case, it's going to come out to 1.48. All right, secondly, if we have use our vertical component, our vertical component is upwards at 0.3, so we'll call that positive 0.3, and anything downwards we'll call that negative. And then if we wanted those to sum up to 0, then this number would definitely be, we'll call this py for the red ball. This one is just going to be negative 0.3 kilogram meters per second. Okay, now we're kind of working in all of our different momentum components for the red ball, and as opposed to having the main component like this one, we have our x and y component. So we're going to go in reverse order of what we did with our blue triangle and make our red triangle and piece it together with these two components. So we have an x component of 1.48, the one that we just got right over here. And then we have a downward negative component for the x that's down at 0.3. Okay, now that I have the vector pointing downwards, I'm going to take the negative off of that 0.3. And then here is our actual resultant vector of what our total momentum is going to be for our red ball. So we could just use Pythagorean theorem and then do a squared plus b squared equals c squared. So 1.48 squared plus 0.3 squared equals c squared. So basically just square rooting both sides. And that gives us 1.51. Okay, so the momentum for the red ball is 1.51. We just use our x and y components to piece them together, make a right triangle, and then our hypotenuse gave us our main momentum of 1.51. Now, if with a momentum of 1.51, momentum equals mass times velocity, the mass of our red ball was 0.5 kilograms. So we can just divide both sides by 0.5. Okay, and then our velocity comes out to 3.02. Okay, so that is our first answer. And then secondly, we want to find our theta. So our theta is going to be right over here. And we want to make sure we use an inverse trig function. I'm going to use the inverse of tangent because tangent is opposite over adjacent. And we have both of those numbers in that triangle already. So opposite 0.3 over adjacent 1.48. Toss that in my calculator. And the theta comes out to 11.48 degrees below the horizontal. All right, so for this problem, you are still using the conservation of momentum, and for this one, we were lucky we didn't have any two-dimensional motion before the collision, but we did afterwards. If you did have some two-dimensional motion before the collision, you would just have to break up the x and y components and then sum those up on the before the collision side, and then sum them up on the after the collision side, and then solve for your unknown from there. But either way, you're still using conservation of momentum and mass times velocity, but you're just definitely using a lot more trig and other math tricks to find your different components. So I hope that was helpful to you in mastering collision problems. Thank you for watching and listening.